Now let's look at the expansion of space again. Here's a bit of space that expands over time. Here are two objects that are distant galaxies, or the Earth and a galaxy, a distant galaxy. And as the space expands, the distance between the Earth and that distant galaxy is expanding. Another way of looking at that is that here's the galaxy and the Earth at some point in time, and they're measured by these measuring rods that are stretched between them. As time goes along, the space expands, the measuring rods don't expand, as we've seen, and that continues to a third point in time. Time equals 3. So the distance between them is expanding. Now we have two other objects here to build on the example. And this could be, for instance, the Earth and a satellite, or a spaceship leaving the Earth at a certain distance. As time goes on, these two objects are becoming further apart and further apart. Now the standard formula to compute the recessional velocity between those two objects is simply the change in distance over the change in time gives the velocity at which they're moving apart. And if, let's say, the spaceship sends a radio transmission of electromagnetic radiation or a beam of light at any point in time back towards the Earth, when the light is finally received at the Earth, there will be a Doppler redshift that's directly proportionate to the velocity at which these objects are moving apart. Now we switch the view slightly to show either of these events from the point of view of a frame of reference where the Earth is stationary. So if we take the Earth as being stationary in this frame of reference, and we're talking about the spaceship moving away from the Earth at time equals 0, it's at a certain distance d1. At time equals 1, it's further away, and at time equals 2, it's even further away. And if the spaceship sent out a signal of light back to the Earth at any point while it had a recessional velocity, when the light is received on Earth, it's received with a Doppler redshift. This diagram also applies if we're talking about the Earth and a distant galaxy that has a recessional velocity. From the frame of reference of the Earth, where the Earth is not moving, the galaxy has a certain velocity at time equals 0, at time equals 1, it has a velocity, and so on. And at any point in that progression, when light leaves the galaxy, later on, when that light is received at Earth, there must be a Doppler redshift that has occurred because of the recessional velocity. Now, someone might be thinking, yes, of course, but the fact that there's a Doppler redshift follows directly from the assumption up at the top that these two objects were increasing in their distance as space was increasing. Now, first of all, that's not my assumption, but rather that is the generally accepted view of physicists and cosmologists at this point in the development of models of the universe. The second thing is, let's look at what would happen if these 2 points were not increasing in distance as space was expanding. So here's a diagram that shows what it would look like with space expanding and the Earth and the distant galaxy remaining at the same distance apart. Now, since we're talking about the distant galaxies that make up the observable universe, let's look at it as if it was on a balloon. So here's a balloon on all the galaxies of the observable universe. So as space expands, space gets bigger, being the surface of the balloon, but the distance between all the galaxies stays the same. So the question then would arise, what's keeping all these galaxies at equivalent or nearly equivalent distances while space is expanding? And there are only 2 answers. One is gravity, and the other is some force that we haven't yet recognized and labeled. Now, there are currently no widely accepted models that would have enough gravity to keep the observable universe together at equal distances while space is expanding, but it's possible somebody could develop one. The final point someone might make, or somebody might be thinking, is what if there are no forces holding these objects at equal distances, and rather they're just sitting there and space is expanding and slipping by underneath them? Well, let's look at that. So here we have the Earth and the galaxy. Over time, space expands. They remain at the same distance. Light travels between them, and as the light travels, the wavelength increases, which explains the observed wavelength. Now, this model amounts to something that's already been investigated, and it's called the tired light theory. The tired light theory says that whenever light travels between 2 objects, the wavelength of the light automatically expands. And the tired light theory has been generally not accepted because it leads to contradictions with observed phenomena and other generally accepted theories and models of physics and cosmology. So, to recap, we've seen that as space expands over time and the segments get longer, the wavelength of light increases during the time the light is traveling, which causes a cosmological redshift in the observed wavelength of the light when it's seen on Earth. We've also seen that at the time the light leaves the galaxy must have a recessional velocity, and there must be a Doppler redshift for the light because of the recessional velocity between the Earth and the galaxy. So, that concludes our look at the expansion of space and the first principles of physics that apply for calculating the Hubble constant. If you're not a physicist or a cosmologist, I recommend you skip the next two video clips and go to the video clip entitled "More on the Equations."